All right, welcome back to another stellar spectroscopy, Chris Churchill's way. Okay, now, like I said, I was hoping to have another homework on, a last homework on the atoms, so maybe we'll wait until after today and then hand it out on Tuesday. Okay, all right, so where are we? We are now finally having, in quite a bit of detail, gone through the atomic structure of the hydrogen atom and understanding its relative transition strengths and its fine structure and the energy shifts and energy splittings. We now want to apply that to multi-electron atoms. And what we talked about was, whereas when we talked about hydrogen, you casually talk about the angular momentum of the electron, the spin of the electron, etc. So in fact, the angular momentum, or you talk about the total angular momentum of the electron, L plus S. In fact, remember that you're always using the reduced mass of the electron. So really what you're talking about is the state of the atom, the spin of the atom, the spin of the total orbital angular momentum of the atom, because you've used a reduced mass on the electron. So the energy itself is really for the whole atom. Therefore, you should move to the next level and think of the angular momentum and things like that really being for the atom. So when you put in multiple electrons and you account for their reduced masses and whatnot, you get these states. You get the spin state for the atom. You get, which is the sum of the spin states of the electrons. You get the spin state, or the orbital angular momentum of the electrons, which is the sum of their angular momentum, which again, of course, is using the reduced mass of the electron, so it's really of the atom. And then you have the total angular momentum, J, which is the sum of the orbital angular momentum and the spin of all the electrons. And again, it's the total angular momentum of the atom. And we have a notation then that we use to describe the atom in a given state, which was 2s plus 1. It's called the Russell-Saunders term notation. Okay, 2s plus 1, Lj, and we said that L was the vector sum of the angular momentum of the electrons, and it had a absolute magnitude of big L times L plus 1, and then we had the total spin, which is the sum of the spins of the electrons, and then we had J, which is the vector sum of L plus S. Okay, and then we had here that the absolute value of L was 0 or 1 or 2 or 3, and so we replaced that with an S, we replaced that with a P, we replaced that with a D, and that with an F. So if I have an atom with S equals 1, L equals 2, and J equals, call it 3, then that would be written as 3, L equals 2 is D, and J 3. Okay. That would be that state of that atom. Okay, called a Russell-Saunders term. Okay. Any questions about that? So when the atom makes transitions, it's going to transition its state. It's going to change from one Russell's Saunders term to another, and we're going to find out that there are selection rules again, like big L can only change by 1, or S can't change, or the parity must change. Okay, we're going to talk about even and odd parity here in a minute too. All right. So having introduced that, I just want to see if this is holding. I wish it would stay. Okay, so we talked about that, and then I introduced to you this diagram here. and I talked about, well, we have a 2-electron atom. How can the L's add? And the thing that you need to understand if you're ever going to do this for real is that L is a vector sum. It's a quantized vector sum. That's a little bit different. It's weird. Okay, so you want L1 and L2 of the 2 electrons. Okay, so let's say that we're going to define this atom as having both its electrons with L equals 1. Okay, capital L is done by vector addition. So the magnitude of L can either equal the difference, L1 minus L2, which is 0 in this case because they're both 1, or the difference plus 1, or the sum. Okay, this could have been the sum minus 1. The point is, you start with L1 minus L2, you keep adding 1 until you get to the maximum allowed, which is 2. So L is quantized and the vector sum is quantized. It's a little bit different than just your regular vector, what's the cosine theta stuff. All right. Anyway, that's what dictates these sort of geometric angles, and then you have, in this case, the angular minimum of the atom for electron 1 in the L1 state and electron 2 in the L2 state. And this is the projection of L on the z-axis for the case that m sub L equals 1, which is this condition that you're seeing, but just rotated. Well, this would be, yeah. And then this is the other possible case, except for that we're selecting L equals 1 instead of L equals 2. Note, there's also the spin, the total spin state related to the L, which gets you J. So that's what this example is. In this case, we're going to assume S equals 1 for our L equals 1 example. So S equals 1, and they could add counter to each other, J equals 0. They could add again to L minus S plus 1, which gives you L equals 1, and they could add as S plus L, which gives you J equals 2. So again, n sub j here, if j is 0, has to be 0. If j equals 1, minus 1 to plus 1, and L equals, or j equals 2, minus 2 to 2. Here's an example of mj equals plus 1, projected here. J processes. Here's your L, and here's your S. Okay. All right. Okay. So this is the vector length of these vectors. Right. But let's move on to this ugly diagram, and I'm not going to go through it in detail. It was an adventure to make this diagram. I had to really prove to myself I understood this stuff to make this diagram. Now, if you can understand what I tried to accomplish with this diagram, that's probably even a greater accomplishment in my understanding enough to make it, because it's probably pretty easy. But here's my point with this diagram, and I'm not going to go through it in detail. This is a 3-electron example. Okay, L1, L2, and L3, and I'm going to assume again that they're all equal to 1. One of them could have been 0, one of them could have been 2, and one was 0, and one was. This is just a 1, 1, 1 assumption. Okay. Okay. So if you assume this configuration where L equals 1, we'll just move forward with that. Here we're going to say we got 3 electrons. Let's assume they're all spin up so that big S is 3/2. Again, this configuration could have been different. This is just the example I chose for a 3-electron atom. Okay? You could make endless diagrams like this for a 3-electron atom, depending on all these permutations. When you take S equals 3/2 and L equals 1, you get this configuration. L equals 1, S equals 3/2, and J equals 3/2. Okay, and then you can say, well, if L equals 1, n sub L could equal minus 1, 0, or 1. So these are the examples for n sub L equals 0, and these are the examples for m sub L equals 1. Okay, and then there's the relative projection of the n sub, I can't see what letter that is, m sub little l's. Okay. And so you can see that you can have these various geometries for this same set of projections and whatnot. And so these are sort of the different vector models that you can get to describe. Yeah. Now, I know it's complicated. It literally would take you a cup of coffee and a half hour probably to really get to the point where you thought you understood the details of this diagram. But it's there for you if you ever get to that point in your life. Chances are, though, you'll have long ago burned these notes and you'll probably looking at them on the web. Well, you're a tough audience. All right. So I just wanted to show you that you can really go to town with the vector model and the projections and whatnot. Now I want to introduce to you the Russell-Saunders term and state symbols. Okay, this is the Russell-Saunders term symbol. It does not include the J, and to this point I have omitted the parity, which is a symbol that goes here. You might see it sometimes. This is why I want to teach you about it, because you'll look and you go, what's that little O doing up there? How come sometimes there's a little O up there and sometimes there's not? Why do I say it that way? Bless you. Because I many times have asked that myself, that question, until I understood it. So now when you see it, you'll know where it comes from. This letter here is the parity, called pi. It basically tells you whether, if you flip the coordinate system around a mirror of itself, whether the wave functions are the negative of themselves or whether they stay the same wave function. Okay. I don't want to get into all the details of that. Okay. So this is the state symbol, L, 2s plus 1 with the parity. Later on, we're going to call it, I believe, the state symbol when we add J, but I've already shown it to you. So the parity is given by this equation here, that pi is minus 1 to some number, which is an integer, either an odd integer or an even integer. Okay? If it's an even integer, this is positive, then it is what they call even parity. Positive, even parity. That means if you switch the axes, the wave functions are symmetric. They're mirror images of each other if you switch the axes. Okay? If it's odd, then this is minus 1, and we call that odd parity. Even odd, based upon whether this is even or odd number. Okay? This number is basically the sum of the L sub i's. Okay? You have 3 electrons, and they all have Li1, then you get lambda equals 3, and you have odd parity. When you have even number of electrons, you always have even parity. And if you have an odd number of electrons, you can get odd parity, depending upon their L values. Yes?
So, how is parity, how does it play into transitions? Does it affect, how many doublets or triplets you have, or, is it...
Actually, that's an interesting way to put the question. It's a good way to put the question. The answer is no. It does not affect the structure of the transitions of the atom at all. It's just a spatial property of the wave functions. But it turns out that when you go through the dipole approximation and you carry through the operators and do the wave functions, because they're either odd or even parity, you find out that when a transition happens under the dipole selection rules, which means the most common types of transitions in the universe, the parity has to change. You have to go from an odd to an even parity, or vice versa.
So it affects the selection rules.
Affects the selection rules. All right. When you go through all of the multiplicities, you can get a table like this. And the thing is, I'm showing you this table. It takes a long time to intuitively be able to just know this table. But this is a reference for you if you want. Now, you have the L term, okay? And then you have the S term. And if you have S equals 0, we call that a singlet. The reason we call it a singlet is because you can only have a single J state, which is going to equal, ta-da, your L. So we call them singlets. Okay. This is why this is 2s plus 1. It's the multiplicity. If S equals a half, 2 plus times a half is 1 plus 1, you get a 2. You can have 2 possible J states. So this number up here is telling you how many possible J states there are, in a nutshell. Okay? So S equals a half, which means you have a 3 up here, tells me that I have 2 possible states up here. Wait a second. This was S equals 1. Sorry, that's this one. And it's a 3, and I have 3 possible. Okay, so here we go. Now again, for L equals 0, it's only J equals a half, just like it was for hydrogen. But when you get to the P state, L equals 1, if you have S equals a half, such that you might have 7 electrons, but they're up, down, up, down, up, down, up, down, up, down, up. Okay, so you have a spin of a half. Okay, then you can have, if you have L equals 1, you can have J equals a half or J equals 3 halves. Okay. Likewise, if L equals 2, it's 3 halves, 5 halves, just like it was with hydrogen, right? And et cetera, et cetera. Okay, what about the triplet states? This is something that we don't have for a single electron atom. Okay, let's say you've got electrons, and it's up, down, up, down, up, down, up, down, up, down, up, up. So S equals 1. These all canceled out to 0. These last 2 added to 1. You can have up to 3 J states. Okay, because you can have L minus S plus 1, and L plus S. So here's the well, except for the L equals 0 state, you can only have the 1, which is 1, which is going to be, again, L plus S. L is 0, S is 1, boom. Then you have L minus S, 0. You have L minus S plus 1 and L plus S, et cetera, as L goes up. Okay, so basically what it's telling you is where in space these numbers can exist. So if you have a 3 here and you have a D, J could be, I just chose J equals 3 here, but I could have picked J equals 2 or J equals 1, meaning I could have had L minus S or L plus minus S plus 1 or L plus S. Okay. Anybody? I'm just trying to give you a feeling for how this plays out. Okay. Well, here we go again. I'm not going to go through it because this is a half-hour lecture in itself. But here's another diagram that shows you the vector addition and how it relates to these terms. Okay? Right. So if we look at this one, we have L equals 2. That's a D state. With J equals 1 and S equals 1. Now, this is equal to the J minus S state. S equals 1. J1 and L equals 2, okay, and so you get, maybe that arrow should go up, I apologize, that was my bad, that arrow should go up, when you sum the J and you get the L, so anyway, and in this case you might have L equals 2, J equals 2, and S equals a half, or equals the 1, you get 3D2, and then here is the 3D3, so remember on that diagram, here's the 3D3, the 3D3 is this configuration where L equals 2. It's adding in the same direction, L plus S, to give you J equals 3. There's your. Any questions about that? All right, so in the end, this is the full term, the Russell-Saunders state term. Now we have the J term as well. Okay. So you can have an O up here for odd, or you can have no symbol, which means even. Okay. I think I show some examples of that. In this case, I drew all even parity guys. All right, now I want to talk to you about multi-electron energy structure real quickly. This is, I'm going to be skipping probably about 80% of these notes because they are highly technical about the ground state configuration of different atoms. And it gets highly technical. It's very difficult. It would be a great homework assignment that would take you hours to figure out, but I'm not going to do that to you. As to how, if I give you an atom to figure out what its ground state Russell-Saunders terms are. Okay, your state terms. So anyway, remember I told you break the Hamilton up into these three parts. The central field approximation is where you only use a spherical blurring out of the potential fields. And when you do that, and you get wave functions that look like this. Okay, this is figure 3.4. So here is hydrogen. You've all seen hydrogen. Basically has a peak out here. This is actually in angstroms. I know that seems a little bit odd, but an angstrom is 10 to the minus 8 centimeters. And if you remember right, the Bohr radius is 0.529 angstroms. Okay, so that's what this line is. It's the Bohr radius. Okay, and you can see it peaks. The wave function peaks for hydrogen there. Okay, if you look at helium, all right, you get a wave function for the inner shell that looks something like that. If you go to neon, you get two shells. Okay, you have some electrons in this thing called the K shell and some in the L shell, and I haven't defined what those mean yet, but then if you go to, say, argon, you have electrons in a K shell, electrons in an L shell, and electrons in an M shell, all right? And you can see how they're distributed relative to hydrogen. So you notice that the electrons that are most boundly tight in argon are way tighter, more tightly bound than the electron around hydrogen. Of course, it has to do with the fact that there's so many more protons. And the broadening of this has to do with the fact that so many of these electrons are shielded from the inner potential from the inner electrons. So this behavior is happening. Now, this is the energy levels as a function of Z, which is the number of charged protons. Okay. Sorry, internet land. Okay. Okay. So this is actually a very, I think, interesting and important diagram. This is the charge of the nucleus. All right. And here is the 2s orbit. You know, the 1s is down here, obviously. This is increasing energy. Here's the 2p orbit, electrons. Now, notice that when you get to about 20 or so here, they become more tightly bound, and then it flattens out again. 3s, independent, 3p, 4d, and then 4s is flat. Notice that there's this period here where if electrons are being filled into an atom, they'll fill up here, 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 and here. So for low Z atoms, the 4s electrons actually will fill their shells before the 3d ones do. But at higher Z, because of this decrease in energy, because of shielding, you actually see that the electrons fill up in this order, and 3d fills up before 4s fills up. You've probably seen that, or you've probably heard that, but you may not have seen a diagram which kind of shows it for you. All right. As you go up to higher and higher, many more electrons, you can see the behavior of these different. Now these are idealized to some degree. They're not exactly perfect. So here's the definition of all those P's, S's, and K's, and L's, and M's. Okay. So, should I make this bigger? It's off the screen a little bit. So you have the principal quantum number N, 1, 2, 3, and then of course you have the angular momentum, 0. 2 is 0 and 1, 3 is 0, 1, 2, and then these are the actual quantum numbers of the actual electrons. Okay, so if you're filling them, if you have say an atom that will take 7 electrons, you put the first one on, it gets the most bound, it goes here. Then the second one comes in and it stays there. They both have K shell, N equals 1, L equals 0, okay, M equals 0, spin up, spin down. We put in the third electron, okay, it can't fit in this particular shell, and that comes from the quantum mechanics, but it can go to M equals 0, L equals 0, ML equals 0, spin up, next one spin down, and then comes over here with a higher angular momentum, it's less bound, and a +1, spin up, spin down, a 0, spin up, spin down, a -1, spin up, spin down, etc., etc. Now, it doesn't actually fill that way. They actually end up filling with spin up, spin up, spin up, and then come back and go spin down, spin down, spin down. And you're like, they do? And yes, they do. We'll talk about that. And then again, you have N equals M, the M shell for N equals 3 by definition, and it fills up boom, 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 and boom, 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 boom. So you can see in this case you have 2 electrons in the K shell, 1, 2, 3, 4, 5, 6, 7, 8 in the L shell, and then this must be 18, 9 squared, 2 times 3 squared, right, 18. You've all probably seen this and understand this to some degree. And then, of course, you get the multiplicity of states are 2n squared, just as they were before. Okay, so here's n, and then this turns out to be 2n squared. That's the multiplicity for that state. And this, ladies and gentlemen, is how the electron configurations populate. So you've seen this notation before. Hydrogen, you have electron in the 1s state. Helium, 2 of them, one in the spin up, spin down. That's the M shell. Then you get to the K shell. You've filled the 1s, so we call that by that symbol to indicate it's a full shell. And then we get to the 2s. So we add a 2s2, we change the spin. Then we add the 2p spin up, and then another spin up, and then another spin up, and then a spin down, and a spin down. And now that we've filled the helium, 2s2, 2p6, what we call K shell, we now move to the M shell. We're starting with sodium. Here's the symbol, meaning this configuration, and onward and forward. And notice, where is it we get to? 3p6 and 4s squared. Yeah, check this out here. There's this neat switch over. It happens at chromium. Fill up 4s squared, 3. Okay, you fill up the 4s. You fill up the 3p. So that's the M shell. Then you go to 4s. Then you fill the 4s shell. Then you start adding the d's at the 3 level, like I showed you. But when you get to chromium, the one that's in the 4s shell moves to the d shell. So now instead of going from, D2, D3, instead of going to D4, 4s2, you go to D5, 4s, D5, 4s squared, D6, 4s squared. You see, and that has to do with that switch over in the energies that I showed you here. And so this whole diagram dictates how they fill.
So why exactly does that happen? Why would it jump down instead?
It has to do with the shielding. All right, it's been a long time since I thought about this, but what happens is that when you want to put that other electron out there, it turns out that the whole energy configuration is actually lower if it goes down to that D shell where that 4s is out there, because of the distance out that the 4s probability peaks. And actually this shielding effect is actually going to be key for understanding ionization potentials as we go down the periodic table. We're going to find out that the periodic table is truly periodic in so many ways. I know you've all seen the periodic table. I am hoping that I will be shedding new windows on that table for you. I'm hoping. Maybe you're all going to look at it and go, yeah, I know all that stuff. Okay, so this is the LS coupling in detail. This is how you calculate all these term symbols for the ground terms in detail. I am not going to go through it. This difference between equivalent electrons and non-equivalent electrons, it's really pretty thick, okay? And it has to do with the different type of Hamiltonians you use, okay? You can see that you're basically, looking at these different states for the different atoms and what their relative energies are for the different Hamiltonian components, and what the LSJ combinations can be, what the electrons are really doing in terms of their m sub L and their spins up or down, and what state terms you get out of those. Okay. It's very involved, okay? But let's just say you can do it. And then what I wanted to do is just introduce to you quickly the alternative coupling scheme. I have now told you about the Russell-Saunders coupling scheme, where basically the angular momenta of the electrons couple together, and then the spin of the electrons couple together, and then they interact with each other. So in other words, the interaction energy of the angular momentum of the electrons that's a high interaction rate for all the angular momenta, and the spin interact with each other at a much higher rate level. But then the spins and the angular momentum at a lower energy level will interact. So they say you sum the L's, you sum the S's, and then you take the spin orbit coupling. Okay, you see what I'm saying? When you get to many electron atoms, that model breaks down. And it turns out it's not the coupling of just the angular momentum of the electrons and the angular momentum of the spins that dominate each other, and then you look at the cross term of interaction of that. What happens is the L and the S of a given electron couple more strongly to make a J. So electron L and S couples with itself most strongly to make a J for that electron. Then you have to sum the J's. They interact. So when you get to much higher electrons couple with their own spin much more strongly than at low number electrons or low Z atoms, where the orbital angular momentum couple more strongly between electrons and the spin couple more strongly between electrons, and then you look at the interaction of those two. Did that make sense? This is called JJ coupling for obvious reasons. The L of S of a given electron I that you're summing over means you're summing over the J's, and you get out the final J, and it's these J's that are coupling. And so the form of the Hamiltonian is different now, because you're, instead of assuming L's couple with L's and S couples with S, and then we couple those, which is Russell-Saunders LS coupling, what we're saying is L couples with S for a fixed electron, L couples with S for a fixed electron. That's the high energy term in the Hamiltonian. Then we look at the cross term energy of the J's. And the reason that is because we would get the energy structure all wrong if we used L plus S coupling. If you crank the Hamiltonian through the wave functions and do the Hardy-Frock, or else if you're way up in some high level atom, this is basically the energy structure you will get. Okay, these are just the relative Hamiltonians that I was talking about. You know, this is the spherical contribution. This is the L, and then this is the L cross S. Okay. Well, this is the L plus L's, and then the S plus S's, and this is then the L cross times S, the spin orbit. Okay. You get this kind of energy structure, and therefore you would get predicted energy transitions of 3 energy transitions for that particular state of this atom, and they would have certain energies given by these energy differences. And you would see a spectrum that came out that would reflect that kind of energy distribution of states. But you don't see that with some of these atoms. You see something that is more like this. So what you do is you actually couple this third Hamiltonian with the spherical one first, which means you're coupling L to S for every electron individually. You get this split. Then you couple the J's of all the individual electrons, and you get this energy structure. Notice that this energy structure is going to produce a very different set of spectral lines than this energy structure. That's how we know that Russell-Saunders breaks down, because the spectrum that it predicts is wrong. Okay? How many people have seen JJ coupling before? One? Awesome. Now I got to hand it to your quantum mechanics teacher. Okay. So, if you ever wondered what JJ coupling is about versus Russell-Saunders, that's what it's all about. So that's the last thing I want to introduce to you. And then you have this group in the middle of the periodic table which have intermediate coupling. So here is your sort of LS coupling with the low electron atoms, and then as you get up you have to sort of mix the Hamiltonians to get these intermediate coupling, and then when you get to the really up to the high electron levels, you're filling the 6p7s shells, you're definitely in the JJ coupling regime. And so this has taken many years for people to work all this out to understand these energy structures. Okay. However, you still, even though you might invoke JJ coupling to understand an atom, guess what? Guess how we still describe it? We'll still describe it in terms of the Russell-Saunders term, because it turns out that you can do this analogously. You see there's 4 levels here. You always end up with the same 4 levels because of the couplings and the splittings, so they're sort of analogous. Now, this is the actual notation you would say. J13 has J2 a half, and then I can't remember what that subscript means anymore. It's been so long since I looked at this. Can't remember what that is. Oh, this must be the J. And these must be the small J's, and these are the big. This is the total J. Okay. So at any rate, you can analogously take the JJ coupling or intermediate couplings and equate them to a Russell-Saunders term. Okay. Now, I am not going to go over this because this is basically multi-electron treatment of transition strengths. Okay, but you start with the Hamiltonian, you work it through your matrix like we did before, you come up with your dipole moment, you come up with an Einstein coefficient. It's just the same. I'm just going to zip through it. You have your Einstein coefficients. Now, I want you to understand that this K prime and K is the change in the state of the atom. That K prime represents maybe D3, and K might represent 3p2. Okay, it's the state of the atom. So they're a little bit different. So anyway, you got your oscillator strengths, and you got your fine structure, transitions, and you got all this stuff in there, yak, 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 yak. And in the end, you get now for the absorption, Einstein B. And then you've got something called term averaging, which I'm not going to cover because we just can't cover everything. But let's look at this diagram. This is, if you go to National Institute of Standards and Technology and say, hey, I want to learn about all the energy possible states and transitions of say, hydrogen, okay? So you will get a table that looks pretty much exactly like that, okay? This is, what are we at here? Table 3.5 on, anybody got the page number here? 95.
95.
Thank you. So, what do we got? And you might be confused by, hey, I just want to know what's the oscillator strength of the Lyman alpha transition, for gosh sakes. But then it's like, well, wait a minute. Lyman alpha transition's a doublet now, isn't it? Yes, it is. Okay. This is the term average, meaning averaged over all the J states of the Lyman alpha transition. Its wavelength is 1215.67004. The ground state energy is, this is the excitation energy, 0. The ground state has excitation energy 0. Always does, always will. That's the floor. The upper state has energy 10.198. Okay. The lower state has a multiplicity of 2. The upper state has a multiplicity of 6. And then here is the Einstein A coefficient, and here is the oscillator strength. Now, but it's really truly a doublet. So really it's the 2s1/2 to the 2p odd parity 3/2. We've seen this before. Now when we did the hydrogen model, we said that's J equals 1/2. And this is n equals 1, n equals 2, n equals 3. And we said this is J equals 1/2, and this is J equals 3/2. Okay, and let's see what we got here. I got this J equals, yes, J equals, this is n equals 3, so it's again, L plus S, so this is 1/2. This is J equals 3/2. Okay. This is S, L, P, so P equals 2. So this is actually 3/2, 5/2. Okay, it's a little higher. So we said Lyman alpha is these two transitions, right? And we, in our old notation, we said, oh, well, this is 1 little s half transition to 2p 3/2. All right. Well, looks sort of familiar, doesn't it? Okay. But now we're saying that the ground state, it's 1 electron, so what's the total spin? Okay, it's in the L equals 0 state because little l equals 0, and it's in the S plus L equals 1/2 state. So we would say that this ground state is S, 2 times 1/2 is 1 plus 1, and J equals 1/2. So that's how you get that. All right. And this state, okay, is basically L equals 1 because it's one electron. Okay, so that's going to give us a P for the Russell-Saunders term. And then we're going to talk about this guy right here. Okay, that is spin is 1 electron equals 1/2. Okay, so J equals L plus S. That's 3/2. Lo and behold, there we have it. That's 2 plus 1. Okay, now, but in this case, because of the p orbitals wave functions, they turn out to be odd parity. There's an O there. Yes?
So are even parities just never written in the Russell-Saunders?
Correct. You just leave them off. Right.
So anytime that you just don't see anything up in the upper right.
You're even. Yeah. So if you see somebody write a transition and the parity hasn't changed, A, they either flubbed it, and you can go, what an idiot. But if they're on the ball and you believe them, what that's telling you is that that was not a dipole transition. That must be a forbidden transition. It must be a magnetic dipole or a electric quadrupole transition, which I haven't really gone into, but you see what I'm saying? So if it's going to be what we call a strong allowed transition, one you typically see in nature, you're going to see a parity change. Okay. So anyway, you can see that the same thing happens with the J equals 1/2. Okay. The other possibility for this one is that J equals L minus S. And that gives you, so this is the upper state, J minus S is the lower state, and that gives you 2p 1/2. So with a single electron, it's easy to make the translation between our old hydrogen only or hydrogenic atom notation and what we call multi-electron Russell-Saunders notation. Right. Now, in nature, you have a bunch of atoms of hydrogen in their ground state. Photons come through, and some of them, in a given, let's pull one hydrogen atom out of the whole ensemble of atoms. Okay, and the photon comes through that atom, and we notice it did this transition. Okay, it did the 2s 1/2 to 2p 3/2 transition. Let's pull another one out. Okay, which one does it do? It has to do one of those two. Let's say, oh, that one also did this transition. So that's 2 out of them. We pull another one out. Ah, what happened? Oh, that one did this transition. Each particular hydrogen atom can only make one of those doublet transitions, right? It's a single atom. Photons come through. It will do one or the other. But what do you see downstream? You see light that's been removed from a beam. Some of that light has this frequency, and some of that light has that frequency. And if you had a super high definition resolution spectrograph, you would see 2 lines, right? But in fact, it's so separated by so little energy difference, 10.198881 and 10.198806 eV, a difference of 0.0000, I don't know what that turns out to be, 44, 47, I can't add, 5, 6, 7, I can't think on my feet, so, oh, I didn't get the job, all right. Anyway, something very small, and the deal is that what you see downstream will be basically blended into one line, And what I'm trying to say to you is that means that it has been averaged over all the atoms that did the stronger doublet and those that did the weaker doublet. Okay, and that is the term, what they call term averaging, because you're averaging over the J states, and the weighting of that has to do with the multiplicity of states versus there versus there. Multiplicity of states is higher over here, so electrons tend to be happier to jump up to that state than they do to the other state. So the ratio is 2 to 1. For every 2 atoms in the gas that jump from here to here, one of them will jump from there to there. Because of the multiplicity of states being higher up there, there's more freedom to go up there. Probability is higher. And so that's what you're going to see then is a weighted blend of that process. This here is the weighted blend of that process. So if you want to know what really goes into a transition from its fine structure, it's this, in the different A coefficients and oscillator strengths. But when you weight them by the relative statistical weights of the upper state in this case, you get that Einstein A and you get that oscillator strength. And that's the one that you're going to pull off the table and use for your spectroscopic analysis. Okay? The term averaged one. Okay. I never understood that stuff for the longest time when I was a wee young astronomer. Okay. So again, I'm trying to say that I'm trying to teach you stuff that I hope will go into your library and remove confusion of so much things about atomic physics when you go to look at it. Any questions about that? Here's my favorite magnesium 2 doublet. Hey, there's the sodium D line you see in the sun. Okay, it's a doublet. Okay, 5891.58, 5897.558. Okay, it's actually ground state. Well, what do you mean? What do you mean that the excitation potential is 0? This is in sodium. How many electrons are there in sodium? I don't know actually off the top of my head. But it's not 1. Did you look it up?
It's 11.
It's 11. Okay, yeah, that's right, because it's right on the chart. 11. There's 11 electrons. Okay. You fill the shells, then your last electron is sitting on all those, above all those electrons. That is now the ground state outer electron. It has an excitation potential of 0. It's the ground state electron. It's not in the n equals 1s state. It might be in the 3s1 state, which I think is where it is. But it's on that's the ground state. If you move it up to 3p, now it's excited. You see? So basically, in sodium, this is now n equals 3. Oh, this is rich. This is 3s. But it turns out it's very, very odd. Oops. A lot of these transitions, n's not changing. Let me do the magnesium one since I actually have a drawing of that for you in the notes, handwritten notes. Okay.
Hey Chris,
Yeah.
why does the silicon 2 have a non-zero ground state? In some of the
Okay, some of these are the ground state ones, and these are slightly excited. So you'll notice that that there's a slight excitation due to the spin state, and it turns out that that energy difference is actually very, very tiny.
So are they not actually in their ground state?
Right. This would be excited excited silicon 2 1194. Sometimes you'll see things like this. Wait, sorry. Like that. Silicon 2 star 1194. That means it's from an excited state. So basically it's telling you you're looking at one of these transitions here. And you'll notice that these wavelengths, in the case of hydrogen, they're very close to each other and blend. But with these other transitions, like for example, even magnesium 2, you'll notice there's a 7 angstrom difference in that transition. That's a lot of angstroms. You can resolve that out and see both members of that doublet very clearly. So in the case of magnesium, you're not going to use the term averaged information. You're going to study this line separately in the spectrum, and you're going to study that line separately in the spectrum. Okay? Now, I'll explain, I'm going to explain this downstream, okay? Which is not in the notes. But if you flip to this page, this is the typical diagram you'll see for magnesium 2 in, say, Lang's astrophysical quantities or something like that. Okay. Notice that what's interesting about this, I'm kind of getting ahead of myself here, but I'm going to go ahead and do it. Getting ahead of the periodic table. Going way to the end here. All right, page 117, diagram 4.7, magnesium 2. Now, this is the classic diagrams that you see for the energy diagrams of multi-electron atoms. I think, and I'm getting this on record, I think they suck. I don't think you can really see what's going on unless you're already like an ace atomic physicist. Let's face it, none of us are ace atomic physicists. Okay? So I've remade my own diagram, which I believe is more better. Okay? Now, with magnesium 2, we're on the periodic table in such a place that, well, I'm sorry, with magnesium, we actually have filled the 3s shell. Okay? It's a closed neutral atom. But when you remove one electron, guess what? You end up having the same electron configuration as neutral sodium. Right? Neutral sodium has a 3s electron, one of them. Magnesium has two 3s electrons. When you remove one electron, you get electron configuration that's the same electron configuration of sodium, neutral sodium, right? And the thing that's different is the fact that there's a different number of protons. So the energy levels are different, but the energy structure is identical. Does that make sense? Okay. So therefore, this is what the diagrams look like for neutral sodium, for singly ionized magnesium, which has one electron removed so that it now has the same number of electrons as neutral sodium, or for aluminum 3. If you take two electrons off aluminum 3, 1, 2, you now have the same electron configuration as sodium, don't you? If you take 4 electrons off of silicon, 1, 2, sorry, if you take 2 electrons off aluminum, you get sodium. If you take 3 electrons off silicon, 1, 2, 3, you have the same configuration of electrons as sodium. If you take off 5 or 4 from phosphorus, 6 from sulfur, etc., etc. Okay. So what I'm saying is that these all, depending if you take off 1 electron, you become sodium-like. If you take off 2 electrons, you become sodium-like. If you take off 3 electrons, you become sodium-like. So that the energy configuration is the same, but the energy levels are different because they have different number of protons defining the potential well. Does that make sense to everybody? That's a very critical thing to understand about the periodic table, and why we say, hey, we have sodium doublets, we have magnesium 2 doublets, we have aluminum 3 doublets, and we have silicon 4 doublets. You ever heard of those talked about? Why? Because they all have this energy configuration which gives rise to these beautiful strong doublets, because they all have the same electron configuration of neutral sodium. Kind of gotten ahead of myself here, but
What's different about them, you said? The transition, the energy is different? Because
right.
of the proton?
The structures are the same, but the energies are different. And that's what I'm trying to show over here. Okay, if you take sodium, these are the energies. Here's the ground state electron and the 3s1 state. Always the same for all transitions because, or atoms. But here's the energy. The excitation level of the 3p state is 2.1 eV for sodium. For magnesium 2, it's 4.4. For aluminum 3, it's 6.6. And for silicon 4, it's 8.8. So basically, this diagram is stretching, if you will. This distance is increasing. And those all change too. But you see what I'm getting at? So one diagram fits all, but the length of these axes change. So what I did was I tried to just demonstrate that by putting these energies out here. Okay. So this is great. Why does sodium have a nice resonant ground state doublet? This actually is the 3s electron, and this is the 3p electron. Same N level. The energy separation now is very large between its 2 eV in sodium between the 3p electron and the 2s electron. Okay. Meanwhile, the rest of those electrons down there in the 2s and 2p shell and the 1s shell, they're not doing anything. They're staying stable. Okay. But the 3s1 electron, the lowest energy state that it can go up to, the smallest excitation, if you will, is to the 3p state. That excitation is 2 eV in sodium. It's 4 in magnesium 2, okay, which is the same electron configuration. So what we do is we see this this doublet, A and B, because we have 2 J states here, which I'm not showing. I can't show everything in one diagram. Okay. Sodium 1, magnesium 2, aluminum 3, sulfur 4. These are called sodium isosequence. They are 1A on the periodic table. Okay, electron configuration. So here is a table of all of those transitions. For transition A, which is the one we say it's a transition from 3s to 3p or 3p to 3s, bless you. Here is the Russell-Saunders notation, and for sodium that turns into be a wavelength from the 3/2 to the 1/2 state of 5891.583, and from the 1/2 to 1/2, 5897.55. For magnesium 2, again, it's the same electron configuration, just a different number, one extra proton in the nucleus. Otherwise, it's the same bloody thing. 2796.352 for 3/2 to 1/2, and 2803, blah, blah, blah. And I believe I may have forgotten to put the parities in there.
They're all even?
No, I forgot to put the parities in there. I think that the parity is odd for the O states. Yep. These should be odd parity. Ah, God, I'll never finish this book. There's always mistakes in it. You can imagine it was a lot of thinking and work to get this put together. Okay. So, right, so you should think of this as being split into 2 different J states. And so this is the 1s even parity, J equals 0, J equals a 1/2 state. And this is either the 2p odd parity, J equals a 1/2 state, or J equals 3/2 state. Okay? And That's what this is trying to show, except I forgot to put the parities in there. I think I'm just going to go jump off a bridge. It's so overwhelming. And then these are all the other transitions that you see, that you might see in stellar spectra and things like that. Okay. Well, I did get a little bit ahead of myself because by teaching you that, I jumped ahead in trying to tell you what the secret weapon is for understanding the periodic table. Okay, so I think we'll have our last class. You're going to be like, thank you, God. Our last class on anything to do with atoms, and on Tuesday, and we'll wrap up the periodic table and understanding what are called electronic isosequences. And I'm going to go through these different diagrams for the, say, calcium 2 and these different families. Now, when I get to silicon, this is to answer your question. Was Jody or Emma who answered the question about the excitation? I'll just show it to you real quick, and then we're going to talk about it when we come back. Right. So when you get to silicon 2 and carbon 2, go back to silicon 2, it turns out that you have these two possible ground states because this energy difference is very tiny. And so you can have, you have two electrons in that shell. One could be spin up, spin down, or you could have spin up, spin down. Or you can have spin up, spin down, or you can have two spin ups. If you are in an environment where there's a little bit of energy around, and then there's an energy state that's just a little bit higher, and you're in an environment that's got some energy, ambient energy in it, you can get that electron up there really easy. And so you get transitions up and down from that sort of just above the ground state excited state. So they call that the excited state transition. And if the electron's in the ground state, then that's the ground state transition.
So it's just slightly above.
Yeah, there happens to be an energy state just slightly above the ground state. It has to do with the spin of the electron and even the angular momentum of the electron. And when you have atoms where you have that, and that only happens in atoms that have two electrons in the valence shell, then you can have that little step. In that little step, then you can get 5 transitions instead of, say, 3 transitions or 2 transitions. Okay? Okay. All right, so it's 5 after. We're good to go, and we're going to wrap up atoms. And you might notice that there's this whole section on line opacities at the back. It turns out by doing this chapter, we covered more than half of that chapter. So stuff that I used to bring back at the end of the class, I instead spent longer period of time in the front of the class instead of talking about breaking it into 2 and talking about the other stuff at the end of the class. But it's the danger of making it seem like it's too much dwelling on one thing, but this is a very important part of understanding spectrum. Have a good weekend.